And let's go. So everybody can see everybody can see this? Okay, great. Let me just minimize that. And like what was mentioned at the beginning, if questions come up throughout the presentation, please put them in the chat for that. And Maggie's going to be looking at the chat, and she can interrupt me if there's something that seems kind of pressing. But hopefully, there's going to be time at the end. Hopefully, this will all kind of make sense as we go. It'll build on itself, and then at the end of the presentation, if there are lingering questions, we can definitely cover specific things. I was hoping to leave quite a bit of time for just questions and answer, to answer questions that people might have. Um, so that was the idea. We're running a little behind schedule now, but let's hope we still have. I'm happy to stay later. Let's hope we have enough time to sort of answer everybody's questions. Okay, so this presentation was built around this concept that when I started farming 15 years ago, it was very common to take a soil test, and everybody did it. And after you received it, it was sort of like, oh, I don't really know what to do with this information. So it was a practice that everybody did, and it wasn't exactly clear what to do with that information. Sometimes you would work with an agronomist. Sometimes you would look at the little graphs that are commonly are printed with the soil test and kind of see if you were in the like low, medium, or high range. There was nothing that I had at that time that really helped to um, explain the numbers, explain the relationships between them, and to get to what an ideal soil levels for different soil types. So I read this book, The Intelligent Gardener by Steve Solomon and Erica Reimer. This is a great book. Talks a lot about sort of the history of organic agriculture and nutrient density. And it was really written for gardeners and farmers with some context, but also with these worksheets in the back that help you translate soil tests into what is sometimes referred to as the ideal soil or the correct mineral balance soil. I'm not going to. So anyway, this is a link. I would recommend looking at this book. I think it's really a good read, and I think it's helps to contextualize a lot of things. But this link here, I'm going to drop this in the chat as well right now. Um, this links just to the worksheets, so it's something that I have saved on my computer, and every time I get a soil test, I go to this link and I print the worksheet. So sharing that with y'all so that you have that too. Um, so this is a soil test. This comes from a lab that I like to use a lot. It's called Logan Labs, and you can see it's a little bit different than a lab or a soil test that you might get from a university system like LSU or Mississippi State. And it has some information. One, there's more information on here, which I think is essential for this process of mineral balancing. And two, it has some information on here that is just not included on a lot of state university tests. I think LSU actually does include this number, which is really of key importance, which is the total exchange capacity, also known as the cation exchange capacity. And you can see that as we go through, that's this number right here, the 5.99. As we go through this soil test, you're going to see how essential that number is in terms of calculating the ratios of minerals that we want to achieve. So just a note about a couple of the things here. Many of us are familiar with how to take soil samples, 6 inches deep and up to sort of 20 samples from a given area, mixed together, and then sent like 2 cups worth into the lab. Um, the cation exchange capacity, now this is a number which is sometimes referred to as the size of the gas tank. So if we think about a soil having a certain ability to hold nutrition, hold different nutrients, um, the number that summarizes how large that gas tank is, how much fuel you can hold in your soil, is this cation exchange capacity. And generally, a low cation exchange capacity is considered below 10, and a high is considered above 10. I mean, that's kind of an arbitrary number, but you can have exchange capacities that are in the 30s or 40s or 50s in some of the richest soils in the country. And you can have soils that are very low in the ones, twos, threes, which are going to be sort of like your beach sands, like your very low organic matter, low clay content soils. So you can see six on this is a sample from my farm a few years ago. You can see six is not terrible, but it's not really that great either. And this is very common for southern soils to have low CEC soils. We have collapsed clays, they don't hold nutrients very well. We have very sandy soil, very weatherized soils. So the ability of soils in the south, this region particularly, maybe not the Delta region, but it is going to be basically low, sort of low ability to hold. And pH is another number that a lot of people under or look at as a sort of general benchmark. Um, the pH is if the CEC, the cation exchange capacity, is the tank size, the pH tells you how full your tank is. So there's maybe beyond the scope of this conversation, how we arrive at this number. But when you do this process of mineral balancing and remineralization, you're going to be adding um, primarily cations, which are the calcium, magnesium, potassium, and sodium. And when you get these four minerals in the correct level in your soil, that's going to automatically make your pH in the 6.5 to 6.8 range, which is ideal most uh, for most mineral release, what we want in our soils. So this lab, Logan Labs, does a little bit of this calculation for you here. That's what we're kind of looking at um, here, where it says desired value, the value found, and the deficit. That's kind of what it's preemptively going through this process that we're going to go through together. So if you don't have a Logan Labs test, you have an A&L lab or a Waypoint, they're not going to do this, but they're going to give you the value found, and then you can plug it into this worksheet. So this worksheet is the one that I linked in the chat. This is the worksheet that I use for mineral balancing, and basically it's just a worksheet that has you transfer over some of the numbers from your soil test into this worksheet. And there's 2 pages. This is the first page. So you can see we've got the total cation exchange capacity at the top, organic matter, pH, and then it goes through all these elements that you've tested. That's what we're gonna do today. We're gonna take that soil test and we're gonna plug it into this worksheet. And on the other end, you're gonna see how we'll have a plan for how to remineralize this area. So this is a zoom in of the primarily the cations that we're measuring in this soil test. So just one note, cations are positively charged ions. Um, these are the things that stick to the clay particles, the silts, the sands, the organic matter that are being calculated in this exchange capacity number. So you have a certain number of exchange sites in your soil on all of those particles in your soil. And if they all add up to 100%, then William Albrecht, who this style of mineral balancing, the agronomist who this style of mineral balancing is founded on, he discovered in his research that there is an ideal number of exchange sites that are occupied by calcium and ideal that are occupied by magnesium, potassium, and sodium. And that ideal is you want 68% occupied by calcium, 12 by magnesium, 3 by potassium, and about 1 by sodium. So when you achieve that, you achieve the greatest number of benefits. Nutrient availability of all the other nutrients seems to work best with this kind of exchange capacity, um, where these cations are filling those slots. You also receive benefits of flocculating soil. So calcium is a double positive, which has this effect of pushing soil particles apart. So you create more airspace in soil, creating more aerobic conditions instead of anaerobic conditions. And if your magnesium levels raise too high, they can have the opposite effect, create very tight soils. So you want to balance these minerals in this way based off of William Albrecht's research. So this is the section that we're going to work with right now. So my included that there. So I'm just transferring over the detected quantities of the calcium, magnesium, potassium, and sodium. So on the soil test, 1,057 pounds calcium, 245 of magnesium, 145 potassium, and 67 pounds of sodium. So that's what's happening there. So now to calculate the ideal level of calcium uh, in my soil, this equation is what we use. So you take the CEC, you multiply it by 400. This number here is the atomic weight of calcium particles. You multiply that by uh, 68%, which is the target level, and you come up with this number right here, 1,629. So our ideal level of calcium is going to be 1,629 pounds. So if we do that again for magnesium, this equation is the same for all four of these cations. The CEC multiplied by the atomic weight multiplied by the percent, and actually that's mislabeled there. It should be 0.12, excuse me, equals the target level. So for magnesium, 5.99 times 240 times 0.12 is 173. Potassium, the same thing. 5.99 times 780 times 0.05. Again, this should be, yeah, no, that's correct there. 0.05, 233. And again, with sodium, we end up with 55 pounds. So now if we're looking at this worksheet, we're just going to transfer that information over. So our actual, what we had measured, 1,059, and our target is 1,629. So pretty self-explanatory. We're just filling out this. And you can see on the worksheet, you have here um, the formula for arriving at the target number. So next step is to calculate the deficit. So you take 1,600, 1,629 and subtract 1,059, and your deficit is 570. And we had an excess in magnesium given our soil type, so we don't have a deficit. We calculate the deficit for potassium. We need 88 pounds, and sodium, we have an excess, so we don't have to worry about that. Okay, so now we move on to the ions. Everything else is going to be measured in parts per million. Sulfur, except for phosphorus, everything else is going to be measured in parts per million. So the way that you calculate pounds per acre from parts per million is that you just multiply by 2. Um, so we're going to convert all our parts per million into pounds per acre, as example here in the sulfur. And then phosphorus is a little different. It's usually, you have to check your soil report, but it's typically recorded in P2O5. So to calculate actual P, this equation here on this worksheet, you multiply by 0.44. That'll give you the percent of actual phosphorus in this molecule of P2O5. So you can see we have a total of 29 P and 32 pounds per acre of sulfur. So we're going to do that for all of our other elements that we have measured here. So we've got the parts per million of sulfur, double it to make pounds per acre. And we've got our calcium, which we've already done. And then we're going to fill in the parts per million of the boron, iron, manganese, copper, zinc on the sheet here. We're going to double those part per millions to get pounds per acre, and you've got your totals there. And then we're going to go ahead and put those in, those get put into the worksheet. That's what we did on the last one. And now we're going to calculate the target for each of these. So if we look at boron, for example, we have 0.54 pounds per acre of boron measured in our soil test. And with a CEC below 10, your target here is 2 pounds per acre. So we go ahead and put 2 pounds in the target rate. Iron is very typically measured quite high on soil tests. Iron, if you have any red in your soil at all, you're likely looking at oxidized iron. Um, the Earth's crust is made up of 4% iron. It's one of the most abundant minerals in the world. And it is often very high on soil tests. So you very likely will not have to be adding um, any iron to your soils. You can see on this test, we have 278 pounds of iron per acre when the target is around 100. You generally don't have to worry about iron as being in excess. So just note if you have enough of it, that's fine. If you need to add some of it, if you have a unique situation, then these are the targets that you're looking for. Manganese, same thing. Manganese on my soil tests were quite high. So I had an abundance of manganese. Copper, I had 1.22 pounds of copper in the soil, and the target is half of zinc. So you calculate that in a little bit. Zinc, we have 13.26. Zinc is calculated at 1/10 of P. So the P target you match. So now this just becomes working with a worksheet. So to find zinc and copper, you need to know your P. Your P is equal to your K. So the K we discovered here is 233. This on this chart says K is proportional to TCEC, and there's a chart down here. It's typically a little higher. For simplicity, I'm just going with my um, calculations. I think the chart on this sheet says like maybe 250 pounds or something, but 233 pounds of K per acre is plenty. And so now we know that our phosphorus target is going to be 233. We know then that our zinc is 1/10 of phosphorus, so 23, and our copper is 1/2 of zinc, so 11.65. So pretty straightforward. I know kind of going through, we're basically just looking at a worksheet and going through it together, but it's not that difficult. Um, this worksheet really like lays it out for you. So then we just calculate our deficits. Okay, so all of our deficits are now filled out in this column here. And we've completed the first page of this worksheet. The second page of this worksheet is like this, looks like this. And its first slot is the deficit for all of these minerals. So we're just going to transfer all those deficits over into this worksheet now. So this is the beginnings of the prescription for what your soil needs in order to get to be completely minerally balanced. So we have a deficit of 54 pounds of sulfur, 200 pounds of phosphorus, calcium, etc. These are the elements that we need to look at in order to mix and add to our soils in order to be balanced in this Albrecht style of mineral balancing. So the question then becomes how to turn this number, like we're going to start with calcium, magnesium, potassium, sodium, how to turn this number into a material applied. So we need 570 pounds of calcium. Um, the worksheet kind of comes with different options for materials to use with their sort of component NPK, sodium, calcium, magnesium ratios. A lot of what we're going to be using for the anions or for the trace minerals, trace metals are going to be in the sulfate form. So you have over here different sulfates, manganese sulfate, copper sulfate, zinc sulfate. These are everything that's listed here is OMRI listed, is organic approved. There's an exception actually. Magnesium oxide is not organically approved or OMRI approved, but um, okay, I take that back. I'm sorry. There are a few things on here that are not organic approved, monoammonium phosphate being one of them, magnesium oxide being another. But I think everything else here is organic approved. Anyway, the idea is that you want to find your short calcium. You want to figure out what material can I use that adds calcium. And there's different materials that you can choose from. Um, as you can see, you could use fish bone meal has a 19% calcium. Crab shell has a 23% calcium, but it also has all these other minerals in it too that become limiting factors for how much you can actually use. The most common by far calcium additive is ag lime, and you can see that ag lime is, depending on the source, 32 to 39% calcium, and it has a little bit of magnesium in it too, 2% magnesium. Dolomite lime is the other very common source of calcium. And you can see here immediately that it's got a much lower percent calcium than ag lime and a much higher percent of magnesium. So this is a good option if you need magnesium. It's not a good option if you don't. And if you recall, we had on our soil test excess levels of magnesium. If I'm going to be using dolomite to get my calcium up, I'm going to be really bringing up the magnesium level as well. So I want to avoid that. That's just an example of how to look at different materials and try to start to formulate ideas of what materials you want to use. So if we look at calcium, um, we're going to do this basic calculation. You take the deficiency pounds of calcium and you divide it by the percent of calcium of the material, and that's going to give you the total pounds needed of the material. So an example of that will be, we're going to use ag lime as our first example. We need 570 pounds of calcium, of actual Ca calcium. Ag lime is calcium carbonate, so you're getting not just calcium, but carbonate as well when you use that product. So only 35, I'm using an average here, 35% of calcium carbonate or ag lime is actual calcium. So you divide 570 pounds by 0.35, and that gives you the number of 1,628 pounds of ag lime. Um, so this is how much ag lime you need in order to raise your soil 6 inches, 1 acre, or whatever size the plot. These are the pounds per acre. This is how many pounds per acre you need to raise 570 pounds of needed calcium. So if we look at our second example and we use dolomite lime, um, you can do the same thing. You can calculate the same thing. 570 pounds, you divide that by 0.22, 22%, and you get 2,591 pounds of dolomite lime. Recall that dolomite lime is a lower percent of calcium per pound of dolomite. So you need a lot more of that material. Okay, so this is now we're starting to kind of think about materials handling. I need to buy, say I'm trying to do 2 acres. I'm going to need to buy, you know, roughly 3,000 pounds of ag lime or 5,000 pounds of dolomite lime. So this is now we're starting to kind of think about the materials that we're going to want to use. If I have to ship it, it would be much better to ship ag lime because I need much less of it than dolomite lime. Um, and then if we continue with that, we're also going to look, since we know that dolomite lime has 13% magnesium, we're also going to calculate the amount of magnesium that we're adding if we were to use dolomite lime. So you do that same calculation, or excuse me, you take 2,591 pounds of dolomite lime that we're going to be adding. You multiply it by 0.13%, and you realize that you have 337 pounds of magnesium that you'd be adding with that product too. So for our situation, dolomite lime doesn't really make sense. We want to not add magnesium. We have an excess of that already, so we're probably not going to use dolomite lime. Potassium is just the same. Every mineral that we're going to go through is going to be the same process. So you take the deficiency pounds of K, you divide it by the percent K of the material, and you get the total pounds you needed of that material. So example one will be, we're going to use potassium sulfate here as our example. Um, Check the percent potassium of potassium sulfate because currently if you buy potassium sulfate from a place like Seven Springs, it's going to be closer to 50% or 51%, I think is what it is. But we're using this percent from the example listed on the worksheet. So we take 88 pounds, we divide it by 0.42, and we get 210 pounds of potassium sulfate. So we need 210 pounds of this material in order to add 88 pounds of potassium per acre. Every sulfate form is going to include sulfur as well. So we want to know exactly what we're putting. If we were to use potassium, we want to know also what is the quantity of sulfur that we're adding in this sulfate form. So sulfur is 17 or in potassium sulfate, sulfur occupy is 17% of the by weight. So if we're using 210 pounds of potassium sulfate, we multiply that by 0.17, and we realize we're also adding 35 and a half pounds of sulfur. Now that's not a bad thing because we actually recall in our um, soil test, we're deficient in sulfur. So this is looking like a really good option for adding potassium because we're getting the potassium that we need and we're also getting the sulfur that we need. Another example of a material that has potassium in it is K-mag or langbeinite. Um, Langbeinite is 18% potassium, it's 22% sulfur, and it's 11% magnesium. So langbeinite is also called sulfol mag. It's just referring to the fact that it's a rock that has sulfur, potassium, and magnesium in it. So when you buy something like that or look it up, it's going to tell you the different percent of these minerals in that rock. 18% potassium, 22% sulfur, 11% magnesium. So if we were to satisfy the 88 pounds of potassium that we need using this material, we divide it by 0.18, not 18 there. We get 484 pounds of Kmag. Because Kmag also includes sulfur and magnesium, you can calculate that out. 484 pounds times 0.22, you're going to be getting 106 pounds of sulfur. 484 times 0.11, you're getting 53 pounds of magnesium. So this would be a good option if you need magnesium and sulfur and potassium. But again, we don't need in our soil test, we don't need magnesium. So it might not be a good option for us. Okay, so this was meant to be like a little like quiz for everyone on the call to use boron as an example. So everybody could just like take a minute and think about this example. So we measured 27 parts per million in our soil test. We convert that to pounds per acre, which is 0.54. And we know from the worksheet that we need 2 pounds per acre. So we're deficient 1 pound and 1.46 pounds of boron. So if we were to choose borax as our mineral that we were going to add, our material that we're going to add in order to achieve 2 pounds per acre, how much, how much borax is needed? How many pounds of borax is needed? Um, so if you're following along, maybe you can just use your calculator or think about this for a second. Think about the equation, what it would be in order to figure out how many pounds of actual borax is needed in order to achieve 1.46 pounds of boron. So everyone's kind of thought about it for a minute. We'll go through it here. Um, okay, so borax is 10% boron. So we need 1.46 pounds. We divide that by zero point 0.1, and we get 14.6 pounds of borax needed. That's all of this is going to be in increments of pounds per acre. The 14 pounds of borax spread over an acre is kind of hard to do. A lot of times when we're doing these mineral balances, you need just very small amounts of certain things, and figuring out how to spread those evenly across the field is a challenge in and of itself. But this is the first step: is figuring out how much we need. Going to go through this last example. Phosphorus is often very low in soils measured on these weak acid tests. So they're often required in large quantities. We're going to use our same uh, calculation here, the deficient pounds divided by the percent of the material, and that gives us the total amount of the material needed. So fructose is a very common soft rock phosphate mineral addition. It's 20% phosphorus. Not all of that is available immediately. It needs to be mineralized over time, but we can still use that 20%. So we need 200 pounds of phosphorus in our soils. You divide that by zero point 0.2, and that's going to give us a grand total of 1,020 pounds of fructose per acre, soft rock phosphate. Second example of this will be bone meal. Bone meal is another common phosphorus addition that you can buy. Sometimes it's cheaper than soft rock phosphate. It's not quite as readily available, and it's also a lower percent of phosphorus. So we'll do our calculation here: 204 pounds. Divide that by 0.13. We get a little over 1,500 pounds of bone meal per acre. So again, if you're making these decisions and you can't buy these things locally, you have to ship them. Um, you're taking into consideration the cost of the material, but also the cost to ship. So these are kind of things that we're looking at when we're trying to make decisions about what materials to buy in order to balance these minerals. So then you just look back onto our worksheet, second page of our worksheet, and after you've done these calculations, you've decided what minerals that you want to use. They make the most sense for you. They're the cheapest, they're the least amount of quantity. You go ahead and you fill out this section here, which is the quantity and materials to add. So I did those calculations for everything. I decided I want to use 1,000 pounds of fructose, 1,600 pounds of lime, 210 pounds of potassium sulfate, 14 pounds of borax, and these copper and zinc. These were the sulfates. We didn't go through those as examples, but we used the exact same formula to figure out how much of copper sulfate we need and zinc sulfate. And so these are the recommendations that we need to follow in order to um, correctly balance the minerals in our soil. Now, it's got this little chart here on the right. I don't know why they don't. It's got sulfur, magnesium, calcium. I don't know why they don't have potassium here as well. But this allows you to basically put the other minerals that you might be adding. Uh, so if we look at zinc sulfate, we're adding 28.6 pounds of zinc sulfate. That's going to include 4.9 pounds of sulfur. With copper sulfate, that's going to be adding 3.5. With potassium sulfate, that's going to be adding 35.6 pounds of sulfur. So you can kind of use, once you decide on the materials, you don't want to discard the other minerals that are going to be included in that. And then you include them here so that you are taking actual account for them. I didn't do that with the lime. I should have done 2% of lime of this ag lime that I'm using as magnesium. That didn't get included here, but it should have been. And then the last one you do is sulfur, because a lot of these materials that we're using are in sulfate form. We're getting a lot of sulfur from these other materials. So you typically do sulfur last. So you can see that it's kind of a blurry picture, but after I count up the sulfur that I'm adding in these other materials, my deficit is actually only 10.5 pounds of sulfur. So if it's only 10.5 because I'm accounting for the sulfur I need from these other materials, then ag sulfur is the most common form of just pure sulfur. It's 90% sulfur. I did my calculation here and found out that I need 11.6 pounds of ag sulfur to get the remaining 10.5 sulfur. So now we have this worksheet and we've calculated everything that we need to add in order to balance the soil. So it's very simple. It's not a complicated process, and it tells you exactly what material you need and in what quantity you need per acre. So that is basically how you take your soil test and you translate it into an amendment sheet. On the soil test, there are included these trace minerals, cobalt, molybdenum, selenium, silicon. It has this estimated nitrogen release, which is closely related to the amount of organic matter you have in your soil. And you have this electrical conductivity measurement here. So the cobalt, molybdenum, and selenium, these numbers all have target ranges too. These numbers don't come from this book. They come from other sources, particularly the Bionutrient Food Association, Dan Kittredge's organization, who's done work in mineral balancing. Um, Sorry, this picture's kind of blurry, but you can see down here, molybdenum, cobalt should be at 2 parts per million, so 4 pounds per acre. Molybdenum should be at 1 part per million or 2 pounds per acre. And you want selenium to be zero point 0.5 parts per million or 1 pound per acre. So those are numbers that I'm including in this presentation for you to include if you're getting down to the sort of um, trace minerals, trace metals, and you want to balance things completely, which I recommend doing. I do that on my farm. So these are this little conversion chart. Not everybody's working on an uh, acre scale, so um, these are just converting, pounds per acre of a material into 1,000 square feet. So y'all can screenshot that or come back to this presentation later or look this up online. It's not proprietary information. It's easy to find, but it helps people who are working in sort of garden scales. Okay, so that is basically the whole presentation, and we're at 11 o'clock, so ran through that pretty quick, which was kind of my goal. Um, and I'm happy to, I know I went through a lot of that kind of quickly. Partly just wanted to make sure that everybody had an opportunity to see start to finish, you take your soil test and then you get your amendment list of what to apply in order to balance. So I wanted to go through and do that so everybody can see that there's nothing fancy about it. It's really just plugging in numbers into these worksheets. You can do, you can learn nothing else about balancing minerals and follow this worksheet, and you're going to be in pretty good shape with your soil. And if you want to continue learning more, there's plenty of things to learn. Material selection is a big one. We didn't talk about, none of this has anything to do with increasing organic matter. For example, there's different mineral amendments that you can use, like humic acid that will help increase your CEC that you can use at small quantities per acre. And by small, I mean maybe 100 pounds an acre per year. Um, it's also not talking about things like materials like kelp, which are broad uh, mineral applications that you can use that have just trace amounts of all 97 known minerals in the world that come from the sea. Sea salt is another amendment that you can use that has an incredible amount of trace minerals. Um, but this is just like bare bones. Like these are the ones that we're testing for in these soil tests, and this is how you know if you're in the right ballpark in terms of the levels, in terms of um, their ratios to each other and their total ratios given the size of this amount that your individual soil can hold. So that is the conclusion of my presentation. I can leave it up. I don't know if yeah, if anybody has questions about anything, I can leave it up and go toggle back, or I can stop sharing too, and we can just have a conversation there. But yeah, I don't know. Maggie, is any questions come in?
We didn't have any questions other than were we going to record it, which I feel like is an important piece of this presentation, just because if folks don't have their soil tests today, then they can go back and kind of go back through the presentation with you when they do have the information. But
For
yeah.
sure.
I also just want to encourage everyone to take down Timothy's contact information. He's an amazing resource, and always willing to answer questions. Has even worked with Sprout on our soil quality, and fertility and health. So yeah, I
Yeah, and if anybody has if they're looking at their soil test and wanting to use this worksheet to balance their soils, and if they want a second eye to look at it, you're by all means, this email account is designed for that. I mean, for people who are in this call that want to ask questions when they're doing this process with their own soil test, you're more than welcome to contact me. I'm happy to look at it and give you my feedback about it. So that's um, I'm happy to do that. And I, the, the thing about the thing about um, soil testing and what to do with the information that you get is um, it just needs to be just demystified. It's not that complicated. And with some sort of basic math equations, you can sort of make decisions as a manager of your garden or your farm that you can make with confidence in terms of what your goals are. Um, there's lots of different strategies. You can do a look at a soil test like this, which came from a plot that we were on my farm that we were hadn't grown in before, and we were preparing to start growing. And our strategy was to just amend with everything that worksheet said that we needed to. Um, we tilled it all into the ground one time, and then our farm is, practically speaking, we're a no-till farm, so we do this large amendment. We went through the path of doing a soil test, doing a large amendment, which meant spending a lot of money up front, but then in subsequent years only having to top off mineral levels, not adding large quantities, um, every year. It was unnecessary at that point. Um, it's totally valid to take the numbers that you get from that worksheet and divide them by three and add a third of the totals of each of those minerals for 3 years. If cost is a consideration, if you're not wanting to till your ground, and so you're wanting the benefit of time to allow those minerals to sort of infiltrate into your ground slowly over time. Um, that was the route that we went in our orchard, which is we're not tilling in that area. And so we were wanting to just add minerals at a slower pace and have them be sort of worked into the soil through the biology and rain and time. So there's as long as you're sort of working towards this ideal level over time, every year theoretically should be getting better, better and better than the last. So application and making decisions around that is sort of separate from just knowing what the actual sort of base amounts that you need are. So this is just helping you figure out what the base amounts are. How big is your fuel tank, your CEC, how much fuel is in your tank, sort of defined by your pH, and then what minerals are missing in order to bring that pH into the range that's ideal for the plants that you're growing, and doing that with confidence, doing that with the feeling that you know exactly why you're putting what down on your farm.
Cool. Thank you, Timothy. I'm gonna say last call for questions. Um,
Yeah, and like I said, just if any questions come up, and you're looking at this later, looking back over this recording, then just shoot me an email or a text or call or whatever. Happy to answer questions. I appreciate everybody coming. And again, sorry for the disaster of the beginning of this presentation. Thanks for sticking around and coming back.
yeah, we appreciate all of you. And luckily, I know a bunch of familiar names on this list. So I know you know who we really are. But with that, I'm gonna stop the recording and we can wrap this call up. Thanks again, y'all.